Everybody, welcome back. So before we dive into the new content for today, let me take a moment to review what we talked about at the end of our class meeting on Wednesday. So recall, I introduced for you this notation Zn, which stands for the set of numbers 0, 1, 2, and so on up to n-1. And I claimed for you that this is an example of a general concept which is going to play a really big role in this class, which is the concept of a group. We're going to meet the precise definition of that concept on Monday, but for right now, the rough idea is that a group is a set that has an operation on it. So in this case, the set Zn has the operation of addition modulo n. Now, before we're ready to meet the precise definition of that concept, I want to take today's video and today's worksheet to meet one more example of a group. That other example of a group, as the title of this video and this slide suggests, is the set of symmetries of a square. So now let me tell you what I mean exactly by symmetries of a square. As I like to do, I'm going to start by defining this concept in a way that's kind of rough, but good for helping us get some intuition, and then we'll come back and make that rough definition a little more mathematically precise. So roughly, a symmetry of a square is any way to take a square and move it around in 3D, so that at the end, it occupies the same space it started in. So an example of a symmetry of a square would be to take that square, pick it up, and rotate it by 90 degrees counterclockwise. So for instance, this corner would wind up here, and this corner would wind up here, and so on. So I've moved the square around, but at the end, when I put it back down after rotating it 90 degrees counterclockwise, it sits in exactly the same spot that it started in. Or another symmetry of a square would be to take that square, pick it up and reflect it across the horizontal axis that I've labeled in yellow. So this corner would wind up here, and this corner would wind up here, and so on. Again, that involves picking up the square, moving it around in 3D, but when I put it back down after doing that reflection, it sits in exactly the same place that it started in. Here's a somewhat more precise way to define what we mean by a symmetry of a square, which also gives us a convenient way to kind of keep track of which symmetry we might be talking about. The idea is to label the square's vertices. In other words, its four corners. And you can label them however you like. I'm going to label them this way: 1, 2, 3, and 4 in those positions. Then with this labeling, I can describe a symmetry of the square as a permutation of these vertices, so a way of mixing them up, that can be achieved by a rotation of the square in 3D space. So that means, in other words, is that if I want to tell you a particular symmetry that I have in my mind, I can do that by keeping track of where each vertex goes. Let me illustrate that with an example to try to make the point a little clearer. Let's say I want to describe for you the symmetry, which is 90-degree rotation counterclockwise. Then I'm going to keep track of where each vertex goes. So for instance, if I look at the vertex 1, after I rotate the square by 90 degrees counterclockwise, that vertex 1 winds up right here. So it winds up at the spot that used to be vertex 4. If I look at vertex 2, then when I rotate 90 degrees counterclockwise, it winds up here, which is the spot that used to be vertex 1. And so on. You can check that vertex 3 goes to the spot which used to have 2, and 4 goes to the spot that used to have 3. So I've specified my geometric idea of 90-degree counterclockwise rotation in terms of this permutation that takes numbers 1, 2, 3, 4 and sends them to other numbers from among that collection. Let's practice that idea one more time, this time with the symmetry which reflects the square across a horizontal axis. Then again with my same labeling, vertex 1 goes to the spot that used to be occupied by vertex 4. Vertex 2 goes to the spot that used to be occupied by vertex 3. And then you can check that 3 goes to 2 and 4 goes to 1. Okay, but all this is way too much to write down, whether we draw it with a picture or we notate it with this permutation of the numbers 1, 2, 3, 4. So we're going to develop shorthand names for the different symmetries of a square. To get us started, 90-degree rotation counterclockwise, we're going to call that R90, and reflection across a horizontal axis, we're going to call that H. And as we develop a bigger toolkit of symmetries of the square in our class meeting today, we'll give those shorthand names as well. Where that shorthand notation is really going to become useful is when we make this observation, which is that two symmetries can be composed, like composed as in composition of functions, and the result will be a new symmetry. Let me use the shorthand notation we have so far to show you an example of that. So let's say I want to take the symmetry H and compose it with the symmetry R90. So I want to do H composed R90, and the first thing to notice here is that I'm using composition of functions notation, which you might remember means that I read it from right to left. So R90 is actually the thing that I'm going to do first. If you'd like, you can take a physical square cut out of paper and try this. Rotate it by 90 degrees counterclockwise, and then take it and reflect it across a horizontal axis. So let's do that sort of drawn on the screen here to try to see what happens. Numbering the vertices here I think is super helpful for keeping track of what's going on. So if I start with my numbering of vertices like this, and then I do R90, in other words, I take the square and I rotate it by 90 degrees counterclockwise, then what you can see is that the 1 will wind up here, the 2 will wind up here, the 3 here, and the 4 here. Now I want to take that square and apply H to it, in other words, take it and reflect it across a horizontal axis. So when you do that, the 1 that was in the lower left will wind up here, the 2 will wind up here, the 3 here, and the 4 there. So there's our composition. Now, if you look all the way from the beginning of this process to the end, what you maybe notice is that vertices 1 and 3 actually wound up exactly where they started, whereas vertices 2 and 4 swapped places. And so what we got in the end of this procedure is the same as what we would have gotten if we had reflected the square across this diagonal axis here. That's a new symmetry. We don't actually have a name for that symmetry yet. Maybe I'll call it D for diagonal. So the conclusion of this computation in that notation is that H composed with R90 is equal to D. So that's all for today's video. In your group work for this class, you'll brainstorm all the possible symmetries of a square and see what happens when you compose them. Don't forget before then to take a moment to try the comprehension question for this video, and then after that, I'll see you in class.